the key to success in solving exponential and logarithmic equations is to identify the kind of equation you're dealing with as a first priority. Now, I don't mean just identifying the equation as either exponential or logarithmic. That's pretty easy. But it turns out that there are actually two kinds of exponential equations and two kinds of logarithmic equations that we have to contend with. Now, I want to show you the four different types of equations here in sort of a degenerate form, because we're really looking for that recognition to get our heads into the concept for solution. Considering the exponential equations, there are two forms. There's one form where we can make the bases look alike and get into the exponential world, and the other kind where we can't make the bases look alike. We have to use another technique to get into the exponential world. All right, in this one, we can actually make the bases look alike by rewriting 64 as 4 cubed. And now that the bases are alike on both sides, we can set the exponents equal to one another and solve the equation. Now, there are some interesting techniques for making the bases look alike. We'll look at some in just a little bit. This generally is the easier of the two processes. All right, here, if we can't make the bases look alike, then in order to get into the exponential world, we use logarithms, because indeed, the world of logarithms is the world of exponents. Now, there are a couple of right ways to do this. We could change this exponential form into a logarithmic form and proceed from there. Or we can take the technique of applying logarithm on both sides. Now, we can apply a logarithm of any base that we want to on both sides of the equation. But since we're making a calculation for a variable and we're going to presumably use the calculator contains either the common logarithmic base 10 or the natural log base e. So we would probably apply one of those logarithms on both sides here. I've elected to use the common log here on both sides. So just logarithm on both sides. You see, that's what we're doing. Now we use our various properties and manipulations to solve the equation. By the power property, x becomes the coefficient of log 2. Now, I think it's more appropriate to think of it right here, though, that log 2 is the coefficient of x. That is, log 2 is just a number in the calculator. So it's just a number as the coefficient of the variable. And we know what we do with those things. In other situations, we divide on both sides by that coefficient. And that's what we do here. We divide on both sides by log 2, leaving x, divide over here by log 2, and now we have a button push on the calculator to find x to be approximately 2.807. Now, we arrive at the same result in this problem if we go from the exponential form to the logarithmic form. And you might try that if you want to. Here, I'll show it to you right quick. It's very much equivalent to this situation. The log form of this, remember, is this. Let's see. We have the log base is 2, the exponent is x, and 7. You see, it seems to be very simple, but in order to evaluate this, we would have to go through that change of base idea. And for the change of base, it would be log 7 over log 2, you see, equals x. And this fraction is precisely the same fraction that we have right here in this other form. It's just a little bit different concept, going from exponential form to log form, or the concept of applying log on both sides. Very equivalent to one another, though, in the end. For logarithmic equations, there are two types. Now, they're pretty easy to recognize as well. One type is where we have the log of some quantity on one side and the log of some quantity on the other side. Now, the other type, just to contrast these two, this other type is the logarithm of a single entity, single quantity on one side, but a real number on the other side. And the approach is a little bit different on these two. Now, to arrive at these two forms, a lot of times in problems like this, you would have to use our properties of logarithms in order to consolidate several terms on one side or the other. Okay, when we have a logarithm of a quantity on both sides and the bases are alike, and that'll pretty much always be the case, we can just set these two values equal to one another. So we just set 2x equal to 36 and solve the equation to find x to be 18. So that's a pretty simple approach. With the log of a quantity equal a real number, though, To solve for x, we have to go into the exponential form. So we would write this logarithmic equation as an exponential equation. It would be 6 squared, the base exponent, equals 4x. Now solve this. 6 squared is 36. Dividing by 4 on both sides, we find x to be 9. I think it's rather interesting that in this one case of solving a logarithmic equation, we actually go into the exponential world. We use an exponential equation. And to solve one type of exponential equation, we use logarithms. So those two different forms, which are inverses basically of one another, kind of go hand in hand and complement one another in the solutions of equations. Well, let's take a few examples that aren't quite exactly like the ones that we had before. We want to first identify our equation in terms of type. This is an exponential equation because the variable lies in the exponent. All right, now the one of two approaches comes into play. We think about, can we make the bases look alike or can we not? If we can't make the bases look alike, we go into the log world. But here we can make the bases look alike. You see, 9 is 3 squared, so we have 3 squared to the x plus 2, or 3 to the 2 times x plus 2. And on the right, 27 is 3 cubed. And we can kick this 3 cubed into the numerator by using a negative exponent, writing it as 3 to the negative 3. Now that the bases look alike, we can set the exponents equal to one another and solve the equation to find x to be negative 7 over 2. Now for this one, once again, we have an exponential equation because the variable lies in the exponent. But this time it's tough to try to make the bases look alike, so we'll jump right into the logarithmic world, which is the world of exponents. So we'll apply logarithm on both sides and just kind of go from there. All right, generally in this technique, this exponent is going to move to the position of coefficient of this logarithm. And away we go. Now, there are, in all of these, I want to show you 3 or 4 different processes in almost every one of these equations, and I just don't have time to do that. If you choose a different way to work these, it's perfectly all right. There are a lot of times 3 or 4 ways to do this correctly. One technique to use here, and I'm kind of using a fast track technique here, which is to get at the isolation of the x minus 3 as quickly as possible. This is just a coefficient. This is just a number. And so if I divide on both sides by that number, which I've done here, then I quickly isolate the x minus 3. Now, another technique from this point would be to take this number and multiply it times each of the terms within parenthesis, which is using the distributive property. But I think that takes up a little more time and it's a little more manipulative in nature. All right, from here, we would just add 3 on both sides to have x equals 3 plus log 9 over log 4. It's just a button push from there, and we would find x to be approximately 4.585. Now, a variation on this theme is this, that occasionally you'll find a situation where you have a coefficient involved with this base of the exponent where the variable lies. You see, the idea here in being able to go into this logarithmic form is that we have a base exponent condition alone over here as a factor. But suppose I had a factor of, let's say, 2 over here with this. Then my first order of business would be to clear the 2. You see, I want to get rid of that 2 first, and then I would go into this technique. The next example shows that situation. Here we have 2e to the x power equals 10. Now don't be too concerned with the e business. It's just a constant, you see. It's just a constant that has an exponent with a variable in it. So we have an exponential equation here. Now we'd like to isolate this e to the x power before we use this idea of logarithm. So we'll divide on both sides by 2, finding e to the x to be equal to 5. Now we want to apply logarithm on both sides. Now we can choose to apply the logarithm of any base that we want to. I'm electing here to apply natural log on both sides. And for a particular reason that we'll see in just a moment, this x becomes the coefficient of ln e. But you see, ln e is simply 1 because we know that when this base, understood to be e, you see, is the same as that number, that this becomes simply 1. So that's the beauty, sort of using natural log when we have e as the base of our exponential function or equation. So at any rate, we have x is ln 5. Ln 5 is approximately 1.609. So we have our answer. Now come back over here for just a second. You might be thinking, well, gee, if it's appropriate to use ln over there because the base of the exponent was e, then why didn't we use a logarithm of base 4 right here? Because we would get that same benefit. Well, let's see what happens. Let's see what happens if we use log base 4. All right, we would have base 4 right here. We'd have base 4 right here. Now, this would indeed become 1. So this would go out, and we'd have no need for all this business. All right, so we'd have x minus 3 equals log 9 in base 4. But what would we have to do to evaluate this? We would have to go through change of base, you see. So we would still have to write this as log 9 over log 4. And then we would evaluate it and add the 3 on both sides, just as we did before. So at any rate, it's kind of an equivalent manipulation here, and I don't think it's really necessary to try to use a base consistent with the base of this exponent, a logarithmic base consistent with the base of the exponent in all of these cases. It is really, though, streamlining things when we have that base of e and using the natural log on both sides. The first thing we notice about this equation is that it's an exponential equation because the variable lies as part of this exponent. Our next task would be to clear all of the factors and elements on this side of the equation except for this base exponent combination. Now to do that, we'll first subtract 5 on both sides, giving us this, and then we'll divide on both sides by 2. When we divide here by 2, we get this. When we divide here by 2, we get 55. Now we're ready to make some decisions about how to attack this problem and get into the exponential world. It isn't reasonable to think that we can make the bases look alike here, so we'll apply logarithm on both sides. We're applying natural log because of this base e. So ln on both sides, this will give us the 2x plus 1 as the coefficient of ln e. Ln e goes out right quick. Now, with a little bit of experience in problems like this, we're not even going to write this ln e. You know, we're going to know that it's, as soon as this becomes the coefficient, that rascal goes out. So why even write it here? It's just unnecessary. At any rate, we have 2x plus 1 equals ln 55. Subtract 1 on both sides. Divide on both sides by 2. And then punching the calculator, we approximate the value of x to be 1.5. Here again, we have a situation where we have an exponential type of equation. We want to isolate this base exponent combination, so we'll divide on both sides by 32. Dividing on the right by 32, we get 20, and on the left we have the 1.5 to the x power. Now we would ask ourselves, can we make these bases look alike? Well, certainly not conveniently. So let's apply logarithm on both sides. I'm using common log now, so I apply common log on both sides. Now this x becomes the coefficient. And this then is just a number in the calculator, the coefficient of x. These are coefficients actually of one another, but we think about it for a solution as a number times a letter. We divide on both sides by the number. So we divide on both sides by this value, we get this fraction, and approximate it to be 7.39. Here's one that, we're going through a bunch of problems very quickly here, but I just want to show you the different looks that these equations can have and go through how we think our way through them, and particularly how to get into the problem at the front end. That's kind of what's important right here. Now here we see this as an exponential equation. The idea is to isolate the base exponent combination as a first order of business. But we have a bit of manipulation to do to accomplish that. And we see 50 times this binomial, and our first tendency from past experience might be to multiply 50 times the 3 and then 50 times this term as well. But you know, if we multiply 50 times this term, then somewhere along the line we're going to have to divide by that 50. So why not divide by 50 right here? You see, that will serve to isolate the binomial to begin with. So just dividing on this side by 50, dividing on this side by 50, the 50s go out here and we have 3 minus e to the 2x. On the right we get 2.5. Now we'll subtract 3 on both sides, and on the right we get negative 1/2. Now we want to clear the minus sign, multiply on both sides by negative 1. to get this, and now we're ready to apply natural log. So apply natural log on both sides, and we proceed as we normally would. Now the 2x becomes the coefficient here. The ln e is out of here, so we have 2x equals this, divide on both sides by 2, and approximate x as 3500ths. Here's a really interesting problem. It's an exponential equation, and it has a couple of terms, though, that involve this base exponent combination where we have a variable in the exponent. The intriguing thing about it is that we can write this in quadratic form. Now watch this, this little routine. We can write this, separating the exponents as e to the x squared, then minus 5 e to the x plus 6 equals 0. Now this is quadratic form because, you know, in quadratic form we have, in our leading term, we have some variable to an exponent which is squared, and then in the next term, in our sort of first degree term, we have that same variable to the first degree. Well, we have that here. We have that. We have some variable, you see the x is variable here, some variable quantity squared, and that same variable quantity here to the first degree. I can emphasize it further by just doing this, if we want to see it that way. But because we can write it in quadratic form, we can change its look quite a bit by performing a little substitution here. We can just say, well, let's let some letter like n, let's say, stand in for e to the x power. And then by making that substitution, it really looks like a familiar quadratic equation. You see, this becomes n squared minus 5n, then plus 6. And we can solve this for n by factoring. We get n minus 3 times n minus 2. And then the zeros become n equals 3 and n equals 2. But do we want to know the value of n? Well, n solves this equation. We don't need the value of n to solve our original equation. We need the value of x. You see, we're looking for that x that is in that exponent. So we have to substitute back. That is, if n is 3 and we know that n was substituted for e to the x, then we back substitute. Replace n with e to the x, and replace this n with e to the x. And away we go with solving these two equations. Well, that's pretty easy. We have, let's say our base here is e, so we'll apply natural log on both sides. So it's ln e to the x equals ln 3, and then x equals ln 3. So x is approximately, turns out to be 1.1. And here, in a similar way, this is ln e to the x equals ln 2. So x is ln 2, or approximately 0.7. Let's turn our attention to logarithmic equations. You know, all of the equations up till now that we've dealt with after those 4 fundamental forms have been exponential, and we've looked at a lot of nuances. Well, now let's go through some nuances with the logarithmic equations. Here we have a logarithmic equation because we see a logarithmic factor here. Now, using the same idea that we did with exponential equations, that idea being that we isolate the base exponent combination. Well, with logarithmic equations, we want to isolate not the term, but the factor involving logarithm on one side of the equation. Now we do see here, and it's important to see, that we have a situation where we have logarithm only on one side and a real number on the other side. So one way to deal with this is to clear this 2 by dividing on both sides by 2. And when we do that, we get this, and then we go into the exponential form. 4 to this exponent is equal to x. And then, let's see, well, the fractional exponent implies a radical, so and the index of the radical is the denominator of the fractional exponent, so this is the square root of 4 to the 5th power. Square root of 4 is 2, 2 to the 5th is 32, so x is 32. Now you might be thinking, what if we had taken a different tactic here? What if we had decided to use our power property and right here, just write this as, now let me give myself a little more room. as log base 4 of x squared. You see, just taking this 2 and moving it to a position of the exponent on x. Now, would that work? Well, let's see if it'll work. Let's see. Now, we're thinking of going now into the exponential form, so we have 4 to the 5th power equals x squared. By the square root property, we know that if x squared is equal to some number like this, then x is equal to plus or minus the square root of that number, you see, of 4 to the 5th power. Now, we know that we can manipulate this rascal into plus or minus the square root of 4 to the 5th, so it looks like we're going to get the same kind of thing that we got before, but it's plus or minus. Now, what about this situation? Well, remember that we can take the logarithm of positive numbers only, you see, and so when we consider these as solutions, we look back here and we say the log of x, can x be replaced with negative 32? No, so we throw that out and use only the 32. Anyway, it's just an alternate technique, but I actually think this one is a bit more efficient. In this next one, we have a rather similar idea, except we don't have a coefficient of this log of x plus 3, so we can go right into the exponential form. The emphasis here is that the understood base of the logarithm is 10, so the base of the exponent is going to be 10. So it's 10 to the 3/5 is equal to x plus 3. To isolate x, we subtract 3 on both sides, and now we simply jump into the calculator to make the calculation for the approximation of x. Now, since this is 3/5, we might find it easier to use the calculator, in using the calculator, to express this as 6/10, but whichever is fine. The approximate value of x turns out to be 98 hundredths. In this equation, we notice that we have a couple of terms involving logarithms on the left and a real number on the right. Our prescription, though, calls for us to have the logarithm of a single entity on one side and a real number on the other side. Well, we can create that situation, though, by using our properties of logarithms. We can bring these two together, where we see that we're adding a couple of items involving logarithms, so we're using the product property. And this is the natural log, then, of the product of 2 times x. So natural log of 2x is equal to 3. Now we jump into the exponential world. We just go from log form to exponential form. Remember, the understood base here is e, so we have e cubed is equal to 2x. Dividing on both sides by 2, we find x to be this fraction. Now we evaluate using the calculator. And to access e, remember that with the calculator, you press second ln. So second ln is e, and then it will prompt you to enter the exponent that appears on e. So enter the 3, close parenthesis, and then you may evaluate this by pressing enter, and then divide by 2, or you can just divide by 2 and press enter to get the value of approximately 10.04. Here's another situation, and in this one we have a coefficient of the log of the single entity, the binomial here. So we would want to clear that coefficient. We divide on both sides by 8, and now we are in the condition that we need to be in order to go into the exponential form. So we would have, let's see, over here, e to that fraction, you see, as its exponent. So it's e to that fraction set equal to 3x minus 2. Now I'm showing this because I just want to show a little more complication in the matter of going from the logarithmic form to the exponential form. But it's handled conceptually in precisely the same way. It's really not that big a deal. It's going to be a big deal for the calculator, and when these things get more and more convoluted like this, the challenge becomes entering it into the calculator correctly. So let's see, we have e to this fraction, and then we want to clear everything but the x on the right. We'll add 2 on both sides to give us this. We'll divide on both sides by 3. And now we need to enter this fraction into the calculator, you see. And that becomes a greater challenge than any of the other parts, possibly. At any rate, we find x to be approximately 1.07. Here's another one now. Notice that logarithms appear on both sides of this equation. And the technique then for solution is to create a situation where we have the log of a single entity on one side, the log of a single entity on the other side, and then we set those single entities equal to one another. So it kind of works like this. We bring these two together using the product property again. This is the log of 2x is equal to the log of 36. And now we can set 2x equal to 36 and easily solve for x. Now, the situation works exactly the same, even if we add the the extra seemingly confusion of maybe a base of, let's say, 7. You see, even if it's base 7, it's not a big deal because we're just going to set 2x equal to 36. The 7 is just not a non-entity, a non-factor here in solving the equation. Now, you might be thinking, well, you know, we can change this into a different kind of problem. We could change this into a problem where we put all of the terms involving logarithm on one side, and then we can solve using the other technique. Well, I wonder if that would be more or less efficient. Let me take the 7s off. It doesn't make any difference, but I just don't want to keep writing them and having to remember to write them from step to step. So I'll just use this. All right, now, here's what I'm talking about. I'm going to kick this term to the other side. Let's see what happens. We have log 2 plus log x minus log 36 equals 0. Now we can bring these together as the logarithm of a single quantity. So it's the logarithm then of, let's see, 2 times x divided by 36. You see it's this, equals 0. And now we can go into the exponential form. Base exponent, so we have 10 to the 0 equals fraction 2x over 36. Now notice it wouldn't make it any difference. It wouldn't make any difference at all if we had a 7 right here. If that base of the logarithm was 7, we'd have 7 to the 0. But anything to the 0 is going to be 1. So we'll have 1 on this side, and on the right, we cancel the 2 with the 36. We get x over 18. Cross multiplying, we find x to be 18, as expected. In this one, once again, we need to go through that process of bringing the logarithms together. And a rather interesting equation will emerge out of this. You see, we don't know where this is going at first glance. We know that we're going to go, we're going to use this technique of consolidation on the left side, and we know that we're going to change it into an exponential equation. But we don't know what that exponential equation is going to look like. Excuse me, we don't know what the equation will look like when we go to exponential form. That's the way I ought to say it, because it's not necessarily an exponential equation. So here we're combining these two by using our product property, and now we go right into that exponential form. So the exponential form, base exponent, so 10 to the 1 is equal to this product. And now this product turns out to be quadratic. So we have a quadratic equation. This is what I was talking about. That when we go from log form to exponential form, we change the form of the equation. We don't know what kind of equation is going to come out, but we just deal with whatever we see. So here we would subtract 10 on both sides, and our prescription here, as you know, is to put all the terms on one side and attempt to factor. If we can't factor, we need to use the quadratic formula for solving it. But here we can factor. We factor this into x minus 5 times x plus 2. We find x to be equal to 5 and x equals 2 as the zeros for this equation. Now, it's important, though, in this situation to discover whether or not we have valid solutions. In this process of bringing things together and changing forms of the equation and so forth, sometimes erroneous solutions may crop up. Let's see if we don't have one here. If x is 5, then let's see, everything seems to be okay up here. We could actually evaluate using the calculator to see if 5 is a legitimate solution, but it does turn out to be one. Now, for x equals negative 2, though, we have a problem because we have the logarithm of a negative number, you see, when x is replaced with negative 2. So we have to throw out this solution. This is not a legitimate solution of the original equation. Now, another way to evaluate the situation is to put this onto the graphing calculator. That is, construct the graph of the equation and look for zeros. We ought to be able to find the solution that way. Well, let's see. Now, this looks a little complicated. Let's see if we can use this version of the equation. So we would take this version of the equation. I've written it over here. And now we would want to put all the terms on one side, you see, by subtracting 1 on both sides and setting it equal to 0. And then we just rewrite it with a y in place of the 0 and to put it onto the calculator. Now, I'm also showing another form of this expression. A lot of times it becomes, the possibility of confusion here exists when we write a number following a log of something complicated like this. And the confusion is that we might think that minus 1 is part of this logarithm business. That is, that it's the log of all of this, and not just the log of that, and after we do that, minus 1. So to take that confusion out, a lot of times this expression would be written as minus 1 as the leading item, and then plus this item. You see, put the number first, and then the logarithm term second. Anyway, it really doesn't make too much difference, but I just want to point that out to you. Okay, let's pop this onto the calculator and see if we can arrive at some solutions. Well, the equation has been entered, and we're looking for a solution at x equals 5. I have set the window for z decimal settings for friendly values when we trace, and here's the graph. Whoa, I'm seeing something funny. I see that we have an x-intercept here at -2. But our solution was supposed to be over here at 5. Well, what's wrong with this picture? Now, it turns out that we have an erroneous solution here. We have that -2 that we threw out, you see, because we didn't use the original equation. We didn't use the original value. Now, the original equation was, and I'm just going to deselect this for the time being, and I may select it in just a little bit, but the original equation was log x plus log x minus 3 equals 1. So I'm going to enter it this way. I'm just going to think about the 1 going to the other side of the equation. And I'll enter log x, then plus log x minus 3, and then minus 1, to throw that 1 to the other side. And now let's see what the graph looks like at this point. Now I'm only graphing this one because I deselected that one. So graph. Okay, I have nothing, no graph appears over here. You see, it was that when we, this is the form that we arrived at by using the product property. We talked about the logarithm of a product, you see. And once we have the logarithm of a product, we have changed the nature of our original problem. And it was that these values, the values of x that are negative, remember, would cause this to be invalid as a solution. We disallowed x being -2 because -2 caused us to have the log of a negative number. But -2 up here would cause us to have a positive value. You see, -2 times -5 turns out to be 10. So it turned out to be valid by looking only at this equation. Anyway, we need to use the original equation for verification purposes. All right, back to the graph. Now, I'm not seeing enough of the graph to the right, but I can get to that point just by pressing trace and just boogieing over to the right a little bit, and it'll kind of make room automatically. The graph will automatically shift over to the point that I'm after. See, when it gets to the edge of the window, it opens the window a little bit wider. I'm going to go further than I need to actually see a crossing point here. And then I'm going to come back to the point of intersection. It should be at x equals 5. Yes, here it is. X is 5, y is 0. This is indeed an x-intercept and therefore a solution to the equation.